Okay, so the first video of our gas law unit is going to cover the properties of gases and especially talking about the kinetic molecular theory. Okay, so in this unit, we're going to be able to use the kinetic molecular theory to describe what is happening and why things are happening for a lot of our other gas laws. So it's important to understand what's going on and what the kinetic molecular theory tells us. Like I said, kinetic molecular theory is going to be able to be used to explain the behavior of gases. A lot of times in a lot of the PowerPoints and a lot of the different things you're going to see from me in class and on these videos is that kinetic molecular theory can also be abbreviated KMT. And you know, as scientists love abbreviations because we don't like to write all day long. Alright, so compressibility. Compressibility is just how much can I compress something, okay? I use the word compress, so maybe let's talk about that a little bit differently. Alright, so I have a volume, alright, I have some matter, I have a solid, you know, liquid, a gas, whatever, and if I start pressing in on it, then I'm increasing, or if I increase my pressure, then I'm decreasing my volume. So the compressibility is just how much can I decrease my volume by applying more pressure. Alright, and we're going to look at that in terms of how that relates to both solids, liquids, and gases. Okay, according to the kinetic molecular theory, gas particles are very small. Okay, and especially they're very small in relation to how much distance there is between gas molecules. So the distance between gas molecules is huge, and then the size is very, very small. So those molecules are small. Okay, because of that, there's a lot of empty space between those molecules. And because of that, I can now decrease that amount of space between them by compressing them. And that's what you can kind of see in this picture that we have here, that as I push down on that piston, so there's a piston there, as I push down on this piston right here, I'm basically just decreasing the amount of space or the volume. So I'm decreasing the amount of space between the gas molecules. Alright, and that's why gases can be compressed a lot more easily than liquids, because you see this liquid, you know, those molecules are going to be a lot closer together. And this is going to kind of show me kind of switching around between things here, but I kind of wanted to show that using this animation that I found on preparatorychemistry.com, which has a lot of really great animations for you to better understand some of the kinetic molecular theory behind the gas laws. I'm going to kind of skip through just a little bit of it. Right here you have a solid. Okay, I'm going to let the solid kind of move. They have a little darker marker molecule in there for you to kind of see how the solid kind of functions. So you see that there's not very much space between the molecules. Okay, so there's not much space, so the molecules aren't really free to move very much. There's not a whole lot of energy in there. As I continually start to increase my pressure, you're going to see things get a little bit faster. But still, you see that little brown marker molecule in there, it's really not able to get away. You know, there's many, many collisions. They're slightly farther apart, so there's going to be a small increase in volume of the solid, but really there's not going to be that much of an increase. You're not really going to see it. But if you keep heating your solid, it's going to become a liquid. You boil or you heat up a piece of ice, what's it going to become? Okay, right, it's going to become a liquid. Okay, with the liquid, the particles do start moving away a lot more. Some of those attractions are getting broken, so the particles are able to move throughout the liquid a lot easier. So you can kind of see that dark particle in there kind of moving around, not really being as restricted as it was in a solid. Eventually, you know, you have water. You heat up water, what happens to it? Give you a couple seconds there. It turns to gas. Alright, you boil liquid, it's going to turn to gas. Alright, so here we have gas particles forming. They're getting so much energy that they're able just to break free from the surface. Okay, so once they're broken free, they're in that gas form, they're moving around in their container, and that's what I'm going to show you right here. Alright, so what you're able to see here is that those molecules are very far apart. They're not close at all. They're very rarely interacting with each other at all. They're bouncing off of the sides of their container. They are, there's so much empty space. So you can just imagine that if I want to get those molecules closer, I can just increase my pressure and push them, push them, push them, push them, push them until they're really close to each other. And you can see that if I go back and I kind of show you the liquid here, I can't really do that. I can start to push and I can compress a little bit, but in the end, I'm not really compressing them that much. You know, there's not a lot of space that I can compress it. I can't get them that much closer to each other. But with the gas, I'm really able to push them closer to each other and therefore compress them. So let me get back to the slides that I have here for you. Hopefully I'm not chatting your ear off, because I think I sometimes have a tendency to do that. All right, so freedom of movement. According to the kinetic molecular theory, basically these particles are not going to be attracted to each other. They're also not going to repel each other. Okay, so we're going to just assume when we're talking about this theory that there's no positive charges, there's no negative charges to attract each other. You know, two positive charges aren't going to repel each other. We're just going to say they don't exist, all right? So that's an assumption that we're going to make when we're talking about kinetic molecular theory to describe properties of gases, all right? So as a result of this, gas particles are free to move as quickly as they want. They're going to move rapidly. They're going to move throughout their container. So, you know, they're going to go at their set speed based on how much energy they have. But the gas particles are going to move freely, expand as far as the container allows. So if they're maybe in a balloon, you know, they're going to expand as far as that balloon is going to allow them to. Okay, kinetic molecular theory also states that gas particles move in straight paths independently of each other. Okay, so they're going to move in their straight path until they collide with something. They might collide with each other. Remember, they're not attracted to each other. But they might collide with each other randomly. They might also collide with the walls of the container. So when they make those collisions, yes, they're going to change path. But for the most part, they're just going to follow their straight path until they make those collisions. And then they'll make their path change. Gases also, for kinetic molecular theory, we're also going to assume that they have perfectly elastic collisions. So when I talk about perfectly elastic collisions, I mean that when they hit the side of the container, they hit each other, they're not going to lose any of that kinetic energy, the energy of movement, that they have. All right, that energy of motion, that kinetic energy that they have. They're not going to lose any of that. They're going to keep all that energy. They're just going to bounce right off of each other. They're not going to stick to each other. They're not going to slow down. That's what you kind of expect when you have, when we're talking about properties of gases. We're going to talk about, over the next several videos, we're going to talk about how these different variables affect gases, and we're going to use them to describe gases. So we're going to use pressure, we're going to use temperature, we're going to use volume, and we're going to use number of moles. And really quickly, I'm just going to kind of briefly go through those really quick and talk about what they are. So gas pressure, what you're really expected to understand about this is that, think of it as my pressure, as I increase my think of it like this, okay? I have my volume, okay? Maybe I have a balloon, and I have it filled with gas molecules, okay? Those gas molecules are going to hit the side of the balloon, okay? Gas pressure is going to be that force of those hits on the balloon, okay? So gas pressure is the force of those hits on the balloon. I can increase that force by doing different things, okay? So I can increase that force and therefore increase my temperature, okay? And I can also cause more hits to happen. If more things are hitting the side, like I increase my volume, more things are going to be hitting the side, and that's therefore going to, or if I increase my volume, less things are going to be hitting the side, and that's going to decrease my pressure. And you're talking about simultaneous collisions of billions of gas molecules with the surface. The symbol for pressure is P. The unit we're really going to use the most is the atmosphere, and the atmosphere is equal to 101.3 kilopascals, or 760 millimeters of mercury. Okay, so those are the different units you're going to see. I'm going to include this in future videos most likely, but I want to go ahead and briefly mention it now. When we're talking about standard temperature and pressure, so if a problem says STP, or standard temperature and pressure, or just standard pressure, it's talking about one atmosphere, or one of these different conversion factors that you're able to make. Temperature. So according to kinetic molecular theory, the average kinetic energy of a collection of gas is directly proportional to the temperature of the gas when measured in Kelvin units. Basically, that's saying if I increase my if I add heat, then I'm increasing my temperature, then I'm increasing the energy. I'm increasing the energy in my gas molecules. Okay, so if I increase the energy in my gas molecules, they're going to move faster. Right? You're gonna see them move faster throughout the container, and that's kind of what you saw in that little animation that I showed you. When we're talking about standard temperature and pressure, and we're talking about temperature, we're talking about a standard temperature of 0 degrees Celsius. So anytime you see standard temperature, it's talking about 0 degrees Celsius, and it's always going to want it in Kelvin units. All right, when we're talking about gas laws, temperature is always in Kelvin units. So whatever your temperature is in degrees Celsius, you need to add 273 to that value. Okay, 0 degrees Celsius equals 273 Kelvin. So if I have 10 degrees Celsius, I add 273 to it. Now I have 283 Kelvin. All right, good. Volume. We've learned this before. You've learned this for years. Okay, it's the amount of space that's occupied by a substance. We're going to measure it in liters or milliliters. For goodness sakes, if you see something that says milliliters or you see something that says liters in a problem, it's talking about your volume. It's not talking about your pressure. It's not talking about your temperature. All right? Get it together. All right? If it says liters, it says milliliters, know that that's volume. If it says Kelvin, it says degrees Celsius, know that that's temperature. If it says one of those units of pressure like atmospheres or millimeters of mercury or torr, know that it is pressure. All right? Know those things. Number of moles, pretty much we're just talking about how many gas molecules, how many gas particles do we have in that system that we're studying. And then lastly, how can you increase the pressure of a gas? We're going to talk about 3 ways. One, I can reduce the volume of the container. If I reduce my volume, I'm going to increase my pressure because I'm going to have more hits. All right, so gas molecules are going to be hitting the inside of my container more often, therefore increasing my pressure. I can also increase the temperature. I can also increase my pressure by increasing the temperature of the gas. So remember, if I increase my temperature, I increase my energy. All right, if I increase my energy, then they're going to hit the sides of my container with more energy, and that's going to cause an increase in pressure as well. Lastly, last thing for the video is if you increase the amount of stuff that's in the balloon, if you increase the number of moles, the number of particles that are in the balloon, if I have more things to hit the side, then they're going to hit the side more often. So that's also going to increase the pressure because there's less room for them to move, and they're going to have to hit the sides of the container a lot more often. So this is the end of the video for kinetic molecular theory and properties of gases. So the next video that logically follows the sequence that we're following in class is next we're going to talk about Boyle's law. All right, so if you know Boyle's law, maybe you don't need to watch that video, but go on to Charles' law or to one of the ones that you don't really understand, but I do highly recommend that you watch Boyle's law. All right, bye.